Stop whatever you're doing, because what I'm about to tell you is going to sound like science fiction, but it's real physics that Oppenheimer proved in 1939, and it still messes with our heads today. There's a type of object in space right now, this very second, that's so dense, so impossibly compressed, that a chunk the size of a sugar cube weighs more than all of humanity combined. And here's the disturbing part that keeps physicists up at night. When Oppenheimer calculated what happens when a massive star dies, when he actually did the math, he discovered that the star doesn't just fade away peacefully like you'd think. It crushes itself. It compresses its own mass so violently that it breaks the rules. And I don't mean breaks them a little bit. I mean it creates conditions where normal physics just stops working, where matter gets squeezed so tight that space itself warps around it like plastic wrap pulled too tight over a bowling ball. You're sitting there right now in a universe where this is happening, where dead stars are creating zones where the laws of nature as we understand them completely fall apart. Oppenheimer saw this coming decades before we had any way to prove it. He looked at the equations and realized something that nobody wanted to believe, that there's a limit, a hard boundary in nature, where if you cross it, you don't just get extreme physics, you get something that shouldn't exist according to everything we thought we knew. And the wildest part? This discovery came from a guy who most people only know because of the atomic bomb. But this work on stellar collapse might actually be more profound, more fundamentally disturbing than anything he did at Los Alamos. We're talking about his collaboration with George Volkoff, their calculations that revealed a cosmic speed limit not for velocity, but for density, a maximum mass beyond which a dead star has no choice but to collapse into something that breaks reality. And if this kind of stuff blows your mind, if you're the kind of person who wants to understand the secrets hiding in the universe that most people never even think about, hit subscribe right now, because what's coming next is gonna fundamentally change how you see stars, death, and the fabric of reality itself. We're diving deep into Oppenheimer's work on stellar collapse, his discovery of what we now call the Oppenheimer-Volkoff Limit, why modern physics still can't fully explain what he predicted, and how the death of a single massive star can create an object so extreme that it literally punches a hole in space-time. This isn't about the atomic bomb. This is about something potentially more profound. His realization that the universe has built-in self-destruct mechanisms that create the most extreme objects imaginable. Objects that exist in regimes where our best theories give up and throw their hands in the air. Now here's what they teach you in school about stars, and it sounds reasonable enough. They tell you stars are these massive nuclear furnaces floating in space, burning hydrogen into helium, giving off light and heat for billions of years. Eventually the fuel runs out, the star cools down, maybe it puffs off some outer layers, and then it just kinda settles into being a white dwarf or something, right? Like a dying ember that slowly fades to black over trillions of years. That's the mental picture most people have. A star lives, a star burns, a star dies. The end. Nice and clean. Peaceful even. The textbooks show you these diagrams where a star gently transitions from one phase to another, like it's following a recipe. Main sequence, red giant, planetary nebula, white dwarf, all very orderly. Except here's the problem, and this is where Oppenheimer comes in. When you actually calculate what happens to a really massive star when it runs out of fuel, when you work through the physics honestly without making convenient assumptions to keep the math simple, you get an answer that seems impossible. See, while a star is alive, it's fighting a constant war. Gravity is trying to crush everything inward. Nuclear fusion is pushing outward with radiation pressure. These two forces balance perfectly, and the star stays stable, sometimes for billions of years. Our sun's been doing this balancing act for about 4.6 billion years, and it's got another 5 billion to go. But the second fusion stops, the second that outward pressure vanishes, because there's no more fuel to burn, gravity wins. And it doesn't just win a little, it wins catastrophically. The entire mass of the star, and we're talking about stars that can be 10, 20, 50, even 100 times the mass of our sun, all of that mass starts falling inward, not drifting, not slowly contracting, falling, accelerating. The outer layers crash down onto the core at speeds that reach a significant fraction of the speed of light. We're talking about 20, 30, maybe 40% the speed of light in some cases. That's around 60,000 miles per second. A sphere of matter the size of a large planet collapsing so fast that the entire process takes less than a second. Less than 1 second for something millions of miles across to compress itself down to a ball maybe 12 to 20 miles wide. Think about that compression ratio for a second. If you could shrink the Earth down by the same proportion, you'd fit the entire planet into a ball smaller than a city block. Oppenheimer thought about this. He sat down with George Volkoff in 1939, and they worked through the equations. And he realized something nobody had fully grasped before. When you squeeze matter that hard, when you force that many atoms into that small a space, you're not just making something really dense like lead or uranium. You're entering a regime where quantum mechanics and gravity start doing things they're not supposed to do together, where the normal rules that govern matter start breaking down. You're creating conditions where electrons get crushed into protons, where atoms cease to exist as separate entities, where the very concept of empty space between particles becomes meaningless because there is no empty space left. Everything gets compressed into a solid mass of neutrons packed together so tight they're essentially touching, shoulder to shoulder, with no room between them whatsoever. A neutron star. And here's where the physics gets really strange, where Oppenheimer made his crucial discovery. He calculated that there's a maximum mass these neutron stars can have. You can't just keep piling on mass forever. There's a limit. Push past that limit, and something else happens. Something that 1939 physics couldn't fully explain, and 2026 physics still struggles with. Picture this, and really try to visualize it because this is the only way to grasp what Oppenheimer was dealing with. Imagine you could stand on the surface of a neutron star. You can't, of course. You'd be instantly crushed into a pancake about 1 atom thick and then vaporized by radiation. But let's pretend you've got some magic suit that protects you. You're standing on this ball that's maybe 12 miles across. Small enough that if you were on Earth you could drive across it in like 20 minutes at highway speed. But this tiny ball weighs 1.4 times what the entire sun weighs. The sun. That massive thing that contains 99.86% of all the mass in our solar system. That thing so big, you could fit over 1 million Earths inside it, and still have room left over. Now compress all that mass down to the size of a city. What does that mean for density? Let me walk you through this in a way that'll stick in your brain. Take a teaspoon, regular teaspoon from your kitchen drawer. Now imagine you could scoop up a teaspoon of neutron star material, just 1 level teaspoon. That teaspoon would weigh about 10 million tons. 10 million tons. That's roughly the weight of 15 Empire State Buildings in a volume that fits in a spoon. To put that in perspective, if you put that teaspoon down on Earth's surface, it would instantly punch through the ground like it wasn't even there, drill down through the crust and mantle, and probably wouldn't stop until it hit the core. The gravity on the surface would be so intense that if you somehow dropped a marshmallow from a height of 1 meter, just 3 feet or so, it would hit the ground accelerating at billions of meters per second squared, and impact at several million miles per hour, releasing energy equivalent to a large nuclear bomb. We're talking about gravity 200 billion times stronger than what you feel on Earth right now. Time itself runs slower there. This isn't metaphor. This is actual general relativity. If you could watch a clock on a neutron star from far away in space, if you could somehow see it, you'd see it ticking noticeably slower than your watch, because the gravity is so strong it literally warps space-time. It curves the fabric of reality so much that time dilates measurably. Light has trouble escaping. Photons climbing out of that gravity lose energy, get red-shifted, arrive at your eyes shifted toward the red end of the spectrum because they had to fight so hard against gravity. This is what Oppenheimer was calculating in 1939, working with George Volkoff, who was his student at the time. They were trying to figure out how dense matter could possibly get, how much mass you could pack into one of these neutron stars before something else had to happen, before the structure couldn't hold. And here's what they found. Here's the calculation that changed everything and opened up a whole new nightmare of physics. There's a limit, a hard ceiling. You can't just keep adding mass to a neutron star forever. At some point, somewhere around 1.5 to maybe 3 solar masses, depending on the exact equation of state you use for neutron matter, the neutron star can't support itself anymore. Even neutron degeneracy pressure, this quantum mechanical force that arises from the Pauli exclusion principle and is supposed to be able to hold up against almost anything, even that incredibly powerful force gives up. The star has to collapse further. But collapse into what? That's the question that haunted Oppenheimer. That's what kept him up at night, working through equations. See, at the time he did this work, black holes were still just a weird mathematical curiosity in Einstein's equations that most physicists didn't think were physically real. Karl Schwarzschild had found these solutions to general relativity back in 1916, solutions that predicted these bizarre objects where space curves so much that nothing can escape. But people thought they were just mathematical artifacts, not actual things that could exist in nature. The idea that an object could compress itself so much that space curves around it completely, that it creates a region where the escape velocity exceeds the speed of light, and therefore nothing, including light itself, can get out. That seemed too bizarre, too extreme to be actual physical reality. But Oppenheimer's math said it had to happen. He and Volkoff calculated this limit, this maximum mass, and the inescapable conclusion was that if you push past it, if you've got a collapsing star core with more than about 3 times the sun's mass, there's nothing that can stop it. It falls right through the neutron star phase, like that phase doesn't even exist. The pressure from neutron degeneracy isn't enough. The star collapses into something where our equations break down, where physics as we know it stops making sense, where the mathematics gives you results like infinite density and infinite curvature of space-time. And here's what I find fascinating about Oppenheimer as a person. He didn't shy away from this result. A lot of physicists at the time wanted to find some way around it, some mechanism that would prevent the singularity from forming. But Oppenheimer looked at the math and said, okay, this is what the equations predict. Let's take it seriously. He even did follow-up work, papers in 1939 and 1940, where he explored what the collapse would actually look like, how it would appear to outside observers, what would happen to light trying to escape from near the surface. He basically predicted black holes in everything but name. And then World War II happened, and he got pulled into the Manhattan Project. And this work on stellar collapse got pushed to the side. But the equations were there, the predictions were made, and decades later, when we finally had the technology to look for these objects, we found them. Neutron stars exactly where the theory predicted. black holes formed from stellar collapse. Everything Oppenheimer calculated turned out to be real. Now let me give you another thought experiment to really drive home how extreme this is, how far outside normal experience we're talking. Imagine you're watching a massive star die. You're in a spaceship at a safe distance, maybe a few light years away, and you've got instruments that can see everything. The star has burned through all its hydrogen, then its helium, then carbon, neon, oxygen, silicon, going up the periodic table as it fuses heavier and heavier elements in its core. Finally, it starts fusing silicon into iron. And that's where it stops, because iron is at the bottom of the nuclear binding energy curve. Fusing iron doesn't release energy, it costs energy. So the core fills up with iron. This ball of iron may be the size of Earth, but weighing more than the Sun. And the fusion stops. Within seconds, literally seconds, the core temperature drops just enough that the pressure can't hold against gravity anymore. And the collapse begins. The core falls inward. Electrons get squeezed into protons, forming neutrons and releasing neutrinos, billions upon billions of neutrinos that go streaming out through the star. The inner core compresses down to nuclear density in less than a second. It becomes so incompressible, so rigid, that when the outer core hits it, the outer core bounces. It bounces like a rubber ball dropped on concrete. And that bounce sends a shock wave racing outward through the star at thousands of miles per second. The shock wave blasts through the outer layers, heating them to billions of degrees, and the star explodes. This is a core collapse supernova. For a few weeks, that single exploding star will shine as bright as an entire galaxy of 100 billion stars. If you could somehow gather up all the light energy that supernova emits, all the visible light, it would be equivalent to all the energy our Sun will emit over its entire 10 billion-year lifetime. And that's just the light. The neutrinos carry away even more energy. In fact, 99% of the energy released in a supernova comes out as neutrinos, not light. We're talking about 10 to the 58th power ergs of energy. That's a 1 followed by 58 zeros. There's no good way to make that number feel real because it's so far beyond human scale. But here's a way to think about it. If you could somehow capture just 1% of the energy from a supernova, you could power human civilization at current energy usage levels for longer than the current age of the universe. That's how much energy we're talking about. And all of it comes from the collapse of a star core down to nuclear density. Oppenheimer calculated this. He worked out the energies involved. And he realized that if the core is massive enough, if it's more than about 3 solar masses, that bounce doesn't happen. The core is too massive. It just keeps collapsing. Through nuclear density, through neutron star density, through any density you can meaningfully describe, it collapses toward a singularity. And this is where Oppenheimer realized something that I think shook him more than people appreciate, something that connects to his later work on the bomb and his whole philosophical journey with physics and power and human responsibility. He discovered that the universe has no safety mechanisms at the extreme end. There's no cosmic rule that says nature can't create conditions so extreme that they break our ability to understand them. There's no law that prevents infinite density. There's no regulation that stops space-time from curving so much that it closes in on itself. When you listen to Oppenheimer talk about physics in his later years, when you read his papers from this period, there's this thread of fascination mixed with discomfort. He found a place where the math works, but the implications seem impossible. His calculations with Volkoff showed that if you have a dying star with more than about 3 times the Sun's mass, and it collapses past the neutron star phase, it keeps collapsing, and collapsing, and collapsing. There's nothing to stop it. No force, no pressure, no quantum mechanical trick. It shrinks down past any size you can meaningfully measure, and the density approaches infinity. Actual mathematical infinity. Not a really big number. Not the biggest number you can imagine. Infinite density. That's what general relativity predicts when you solve the equations honestly. A singularity. A point of literally infinite density, where space and time curve infinitely, and all our physics equations spit out nonsense answers like infinity and undefined. Now, you're probably thinking this sounds exaggerated, like maybe the math is just breaking down because we're using the wrong equations or pushing them too far beyond where they're valid or something. That's what a lot of physicists thought at first, too. They assumed that once you got into these extreme regimes, quantum mechanics would kick in and somehow prevent the collapse. That nature would find some clever way to avoid the singularity, some mechanism we hadn't thought of yet. Maybe exotic matter with negative pressure. Maybe a phase transition to quark matter. Maybe something. But here's the thing. We've looked. We've built better theories. We've refined the calculations with modern supercomputers. We've incorporated everything we've learned about particle physics and quantum field theory. And as of 2026, the best physics we have, our most sophisticated models, still say that beyond the Oppenheimer-Volkoff limit, collapse to a singularity is what the math predicts. Black holes are real. We've photographed them. The Event Horizon Telescope got that famous image in 2019 of the supermassive black hole at the center of the galaxy M87. We've detected gravitational waves from stellar mass black holes merging, these ripples in space-time that match exactly what general relativity predicts from black hole collisions. They exist. They're out there. And they're every bit as extreme as Oppenheimer's math predicted back in 1939. Before I get to the most disturbing part, the part that still keeps physicists awake at night, tell me in the comments what city or country you're in, what part of the world you're watching from. I'm always curious how far this reaches, how many people across the globe want to understand this stuff, want to know what's really happening at the extremes of physics. But yeah, back to what Oppenheimer discovered. He found that stellar death isn't gentle. It's not poetic. It's violent and extreme, and in the most massive cases, it creates objects so dense that they literally tear holes in the fabric of space-time itself. The event horizon of a black hole isn't a physical surface like the surface of Earth or a neutron star. It's a boundary in space, an invisible sphere around the singularity, where a very specific thing happens. The escape velocity equals the speed of light. Inside that boundary, every direction you can point, every path through space, every possible trajectory you could follow, all of them lead deeper into the black hole. Not because there's some force pulling you in once you cross, but because the geometry of space itself has been warped so severely that the future direction of all paths points inward toward the singularity. Time and space actually swap roles inside the event horizon. Moving forward in time becomes like moving toward the center. You can no more avoid hitting the singularity than you can avoid moving forward in time right now. Oppenheimer saw this in the equations. He worked through the Schwarzschild metric, the exact solution to Einstein's field equations for a non-rotating black hole. And what bothers physicists today, what still doesn't have a complete answer, is what happens at the center. What actually happens when you compress a star's worth of matter, maybe 10 or 20 or 30 times the mass of the Sun, down to a point smaller than an atom? According to general relativity, the density becomes infinite. The curvature becomes infinite. Time stops in a certain sense, or becomes meaningless. We don't know. Oppenheimer didn't know. And 7 decades after his death, we still don't have a complete theory that works in those conditions. We have general relativity, which works great for large scales and strong gravity. We have quantum mechanics, which works great for small scales and particle physics. But we don't have a theory of quantum gravity that successfully combines both. And black holes, especially the singularity at the center, exist precisely in the regime where you need both: strong gravity and quantum scales. That's the problem. Here's what got to Oppenheimer, and I think this connected to everything else in his life: all his later moral struggles with the bomb and his role in unleashing destructive forces on humanity. When you look at the universe honestly, when you follow the math wherever it leads without flinching or making convenient assumptions, you find that nature is way more extreme than human intuition can grasp. Stars don't just burn out peacefully like candles. In the right circumstances, when they're massive enough, they detonate with energy output that briefly outshines entire galaxies containing hundreds of billions of stars, then collapse into objects so dense they break the equations of physics. And this is happening right now, as you're sitting there watching this video. Somewhere in the universe, this second, a massive star is running out of fuel. Its core is about to collapse. In less time than it takes you to blink, that core will compress from the size of Earth to the size of a city, releasing more energy in neutrinos alone than our Sun will emit in its entire 10-billion-year lifetime. The outer layers will rebound off the incompressible core and explode outward as a supernova. And if the core is massive enough, if it crosses that limit Oppenheimer calculated with Volkoff, what's left will keep collapsing. It'll fall through the neutron star phase like it's not even there. It'll compress past any possible mechanism of resistance we know about and form a black hole. And here's what this means for you, for your existence, for why you should care about stellar death. Every atom in your body heavier than hydrogen and helium was forged in a star. The carbon that forms the backbone of every organic molecule in your cells, the oxygen you're breathing right now, the nitrogen in your DNA, the calcium in your bones giving them structure, the iron in your hemoglobin carrying oxygen through your blood, the phosphorus in your ATP molecules storing energy. All of it, every single atom of every element heavier than helium, was created by nuclear fusion in the core of some massive star billions of years ago. And that star died. It almost certainly died violently. Maybe it went supernova and scattered those atoms into space, where they eventually condensed into new stars and planets. Maybe some of your atoms came from multiple different supernovas. Maybe the iron in your blood was forged in one stellar explosion, and the calcium in your teeth came from a different one millions of years later. But that death, that catastrophic stellar collapse, is part of your origin story. You exist because stars die in the most extreme ways possible. You are literally made of star death. Oppenheimer understood this deeply. He understood that creation and destruction at cosmic scales are inseparable, two sides of the same process. The same physics that makes life possible, that creates heavy elements necessary for biology through stellar nucleosynthesis, also creates supernovas and neutron stars and black holes and objects so extreme they defy understanding. There's no way to have one without the other. The universe doesn't give you life-generating stellar fusion without also giving you death-dealing stellar collapse. They're part of the same package. And I think that realization that nature is fundamentally extreme and violent at its core, that there are no gentle options at the boundary conditions, that physics permits and even requires these catastrophic events. I think that shaped how Oppenheimer saw everything else. When he later worked on the atomic bomb at Los Alamos, when he led the team that unleashed fusion and fission on a human scale, He was in some sense just following the same physics he'd studied in stars. The universe had already shown him that matter contains absurd amounts of energy locked inside it. The mass-energy equivalence, E equals mc squared, works the same way in a star as in a bomb. A tiny mass can release devastating power. The laws of nature permit extremes beyond human comprehension or control. He'd seen it in the death of stars. He'd calculated it in his papers on stellar collapse. The bomb was just applying the same principles at a smaller scale, bringing stellar physics down to Earth. And when the Trinity test succeeded on July 16, 1945, when that first atomic bomb detonated in the New Mexico desert at 5:29:45 in the morning and lit up the pre-dawn sky brighter than a dozen suns, Oppenheimer famously quoted the Bhagavad Gita, "Now I am become death, the destroyer of worlds." But I wonder if in that moment he was also thinking about his stellar collapse calculations from 6 years earlier, about how he'd proven that the universe itself is a destroyer of worlds, that stellar death crushes entire solar systems worth of matter into singularities, that nature itself has no problem with total annihilation. He didn't invent destruction. He just learned how to do it on a human scale. What modern physics still can't fully explain, what keeps theoretical physicists working on this problem in 2026, is what happens inside the event horizon. We can calculate what the collapse looks like from the outside. We can predict the formation of the horizon with incredible precision. We can predict the radiation that gets emitted, the gravitational waves that ripple out through space, the space-time curvature around the black hole. But once you cross that boundary, once you fall past the event horizon, our equations encounter fundamental problems that we haven't solved. General relativity says the matter keeps collapsing to infinite density at the singularity. The math is clear on this. You fall toward the center and the tidal forces grow without limit, and eventually you hit a point of infinite curvature. But quantum mechanics says you can't have infinite density because the Heisenberg uncertainty principle prevents exact localization of particles. If you try to confine something to an infinitely small region, the uncertainty in its momentum becomes infinite, which means it has infinite energy, which creates more mass, which makes the problem worse. So which theory is right? Neither. Both in some way we don't understand yet? This is the information paradox. This is the quantum gravity problem. This is where two of our most successful theories, general relativity, which has passed every experimental test we've thrown at it, and quantum mechanics, which has been verified to ridiculous levels of precision, give contradictory answers about the same physical situation. And it all traces back to what Oppenheimer calculated. He found the limit where normal physics stops working. He predicted that objects would form that exist in regimes where our best theories conflict and contradict each other. And he was right. We've found those objects. We've measured them. We've detected gravitational waves from black holes with masses 30, 60, 100 times the Sun, well past the Oppenheimer-Volkoff limit. We've found supermassive black holes at the centers of galaxies with masses millions or billions of times the Sun. These things are real. They're out there. And the fact that we can't fully explain what's inside them, that our physics breaks down precisely where Oppenheimer predicted it would, that's not a failure of his work. That's validation. He identified a genuine boundary in our understanding, a real edge where our maps of reality stop making sense. The death of a massive star creates conditions so extreme that space and time themselves become twisted beyond our current ability to describe mathematically. And think about what that means. This isn't some abstract mathematical game physicists play on blackboards. This is physical reality. Right now, as you're watching this video, There are millions of stellar mass black holes in our galaxy alone. Conservative estimates put the number at around 10 million to 100 million. Most of them are just sitting there quietly, not consuming anything, not emitting light, invisible except for their gravitational effects on nearby stars. But they're there, scattered through the Milky Way. And every single one represents a place where physics as we know it has a hole in it, a blind spot, a regime where we can describe what happens outside the event horizon, but not inside. Oppenheimer discovered this in 1939, before computers, before we'd even confirmed that general relativity's predictions about things like gravitational lensing and time dilation were accurate, before we knew that neutron stars were real objects and not just theoretical possibilities. He did it with pencil and paper and pure theoretical reasoning, sitting down with George Volkoff and working through the equations of hydrostatic equilibrium and relativistic degenerate matter. And almost 90 years later, we're still grappling with what he found. String theory tries to address it. Loop quantum gravity tries to address it. Various approaches to quantum gravity are all trying to figure out what happens at the singularity, whether it's really infinite density or something else. But we don't have a final answer. We don't have a complete theory. The problem Oppenheimer identified is still open. So next time you look up at the stars, next time you see those peaceful little points of light scattered across the night sky, remember what's really going on out there. Some of those lights are massive stars burning through their fuel at incredible rates, destined to die catastrophically within the next million years. Some of them might have already died, and we're just seeing old light that's been traveling toward us for thousands or tens of thousands of years. Light that left the star before humans built pyramids or invented writing. And scattered through the darkness, invisible to our eyes but detectable by their gravity, and the way they warp light passing nearby, are the remnants. Neutron stars spinning hundreds of times per second, with magnetic fields trillions of times stronger than Earth's. Black holes warping space-time around them so severely that they create gravitational lenses that bend and distort the light from galaxies behind them. Regions where stellar death has created conditions so extreme that Oppenheimer's equations start to break down, and modern physics, with all its sophisticated mathematics and experimental validation, still can't tell you exactly what's happening. The universe isn't gentle. It's not designed for comfort or easy comprehension. It's not tailored to human intuition or what makes us feel safe. It's a place where massive stars crush themselves out of existence in fractions of a second, where matter can compress to densities that make our equations give nonsense answers, where the very geometry of space can be so warped that time and space trade places and singularities form. Oppenheimer saw this. He calculated it carefully. He published it in peer-reviewed journals. And in a very real sense, he never escaped what that taught him about nature, that the universe permits extremes beyond human scale, that the laws of physics allow for total annihilation, that there are no cosmic safety rails preventing reality from creating conditions too extreme to understand or survive. The same math that governs a gentle sunrise also governs the catastrophic collapse of a star core. The same physics that lets you exist also creates black holes. There's no separation. It's all one unified set of laws that permit both creation and destruction, both stability and catastrophe. Can you look at the stars the same way after knowing what's really happening when they die? Can you see the night sky as peaceful when you know that stellar death is violent and ongoing and creates the most extreme objects in the universe? If this video changed how you see stellar death and the extreme physics hiding in space, if you're sitting there with your mind expanded and maybe a little disturbed by what the universe actually does, smash that like button so I know this stuff resonates with people. And if you want to keep discovering the physics that doesn't usually make it into textbooks, the calculations and discoveries that reveal just how strange and extreme the universe really is, hit subscribe and turn on notifications because there's new revelations every single week. Comment which aspect of Oppenheimer's work you want me to explore next. Maybe his quantum tunneling calculations that explained radioactive decay, or his early work on cosmic rays, or the specific physics he used at Los Alamos to calculate critical mass. Let me know what you want to see. Thanks for watching. Thanks.